Hello, I'm Jongkyun Park, belonging to Professor Sungcheol Kim's lab. I'd like to say thanks for giving me a chance. Let me start my presentation of fifth order harmonic generation in solids from direct nanoparticles for my PhD defense. The presentation was prepared with the introduction, nanoparticle harmonic generation, and summary. In the ultra-fast optics, the demand for UV and UV range pulses has been increased recently because their high photon energies can facilitate better spatial and temporal resolutions than commonly used titanium sapphire lasers, allowing more advanced scientific and industrial applications. The UV pulses are usually generated in two ways. One way is using synchrotron radiation, but the synchrotron accelerators are large-scale facilities with very limited accessibility and high experimental cost. Another method is the high harmonic generation process. If a very strong laser beam is focused on to uh, target medium such as gas atoms or solids, high harmonics with higher photon energies than the driving laser can be obtained. This process is high harmonic generation. If a harmonic has 5 times higher photon energy, it is called fifth order harmonic. The process is widely investigated because it can provide UV pulses in normal laboratories. During my PhD, I have mainly studied high generation using solids. Let me explain the process in solids. The pictures describe the process in terms of real and momentum space, respectively. Generally, momentum space is used for the description when an intense laser is focused onto a solid target. An electron is excited to conduction band. Uh, Due to strong field excitation. Then it is accelerated by laser fields along the conduction band, and finally it recombines with a neighboring hole on valence band. Several studies this have demonstrated that the electron's motion leads to the high harmonics generation. Many studies of harmonic generation have been focused on increasing the harmonic intensity, mainly facilitating metal-based plasmonic structure or dielectric structure. When the beam is incident on the metal-based plasmonic structure, surface plasmons, which are collective oscillations of conduction electrons, are induced, exhibiting a high field enhancement, leading to harmonic output enhancement. On the other hand, when a driving laser is incident on a dielectric nanostructure, an abrupt change of physical parameters at the dielectric surface boundary uh, can induce locally field enhancement, leading to uh, harmonic output enhancement. Even though each method has distinct characteristics, dielectric's high damage threshold make us interested, and we tried to incorporate the dielectric nanoparticles into high harmonic generation for output enhancement. In order to perform experiment confirming the nanoparticle effect, firstly we fabricated nanoparticle samples through solvent evaporation method. The process is mixing Al2O3 nanoparticle solution and water, sonicating the solution for nanoparticle dispersion, dropping the solution onto the substrate, and evaporating the solvent with a hot plate. Even though it is challenging to control the sample characteristics, the method enables simple and fast sample fabrication. To generate harmonics, the experiment setup was constructed as shown in this picture. The measurement process proceeds as laser beam pulses from the titanium sapphire oscillator enter the vacuum chamber. Then the pulses are focused by a focusing range onto a solid target, resulting in high harmonic generation. The high harmonic beam arrives at the optical grating, which reflects each harmonic at a different angle onto the MCP. Then finally, the UV beam image on the MCP is recorded and analyzed. The first experiment was designed to confirm the difference in harmonic yield between the nanoparticle samples and the bulk materials when the same laser pulses are used. In the experiment, the fifth harmonic induced from Al2O3 nanoparticle sample, bulk quartz and bulk Al2O3 with the same laser pulses was recorded to compare each output. The figures represent the measured signal. According to the result, nanoparticle samples showed 67 times higher fifth harmonic yield than the bulk Al2O3 alone. The graph depicts the measured harmonics from the nanoparticle and bulk substrates as a function of infrared intensity. The black lines are nanoparticle samples. Blue and green lines are bulk Al2O3 and quartz. All harmonics scale with the laser intensity, and the conversion efficiency was highest for the nanoparticle sample, followed by the bulk Al2O3 and quartz. The result clearly shows significant enhancement of the harmonic yield by introducing nanoparticles. The second experiment was designed to investigate whether the measured fifth harmonic originated from the nanoparticle or the substrate. For that, we used nanoparticle samples on fused silica and quartz substrates. Although both materials have the same chemical composition, SiO2, the fused silica is amorphous, having an isotropic band structure, while the quartz is crystalline, having an anisotropic and full symmetric band structure. Thus, if the fifth harmonic originated from the Al2O3 nanoparticles only, it should show a uniform yield as a function of laser polarization because the used nanoparticles are fully crystalline. Namely, this experiment can distinguish between the contributions of the SiO2 substrates and the nanoparticles. For example, in the case of Al2O3 nanoparticles on a quartz substrate, if the fifth harmonic intensity shows periodic modulation as a function of laser polarization, it means the fifth harmonic contains a contribution from the substrate. On the other hand, if the signal intensity is independent of the incident laser polarization, the fifth harmonic originated from the nanoparticles only. In the experiment, we recorded the fifth harmonic yield from the fused silica and quartz substrates with and without nanoparticles. The graphs show the recorded fifth harmonic signals from the bulk fused silica, bulk quartz, and nanoparticles on the fused silica and quartz substrates at substrate angles of 0 and 45 degrees as a function of the laser polarization angle. Several important conclusions can be made from these results. In the case of the physical substrate with and without nanoparticles, the fifth harmonic output should be uniform, regardless of the polarization angle and substrate orientation. Because physical is an amorphous material, but we observe a modulation with a 180 degrees periodicity as a function of rate polarization for any substrate orientation. This is caused by the reflection efficiency of the optical grating, which is strongly polarization dependent. So the signals can be considered uniform like this. Next, next, for the quartz substrates with and without nanoparticles, periodic modulation by its crystal symmetry is clearly visible. In addition, the polarization modulation is shifted by 45 degrees when the substrate is rotated by 45 degrees, confirming the crystal symmetry as the source for the periodic modulation. Consequently, this result suggests that the measured fifth harmony contains a large contribution from the substrate. The previous experiment suggests that a large portion of the fifth harmony is generated in the substrate. To investigate the harmony gate in this situation, it is useful to refer simulation results. The figures show the simulated field distribution when a titanium sapphire ray passes through an 800 nanometer diameter nanoparticle sample. The E-field at the direct interface is expected to be enhanced by a factor of 2.4. Considering some recent research on high harmonic generation from solids, reported that the high harmonic output can increase by 1 to 2 orders of magnitude when the field is doubled. So it is conceivable that the increase in the fifth harmonic yield is caused by the field enhancement around the interface. Lastly, let me summarize the presentation. We performed the initial experiments, providing a preliminary characterization and feasibility demonstration of nanoparticle high harmonic generation. Through the experiments, notable pointers were identified. For example, the generation of EUV range harmonic and significant enhancement in the high harmonic yields was confirmed in the nanoparticle samples. The enhancement was caused by the E-field amplification at the direct interface. These studies confirm the feasibility of the nanoparticle high harmonic generation and will pave the path to a deeper understanding of the high harmonic generation process in solids. During my PhD, I published 5 papers. Thanks for your attention.